Okay, so this multiple choice, really important that you understand what's going on here with these multiple choice questions. The test is going to be 20 multiple choice. I don't think there's the FRQ on it, okay? So we want to make sure we follow all of this logic here. Here we go. All right, so problem number 1, it says find the expected. So we want to find the expected value right there. And here's the issue. They did not give you any information. They did not give you numbers in this section so that you could go put it into your calculator into matrix A. And then go run the test and then see what's in matrix B. All that they ended up giving you was just the totals. So because of that, it forced you to know this formula of how to get expected values without actually running the chi-squared test on your calculator. So it forced you to have to do this by hand. So they wanted the expected for this. So you did the row total of 31 times the column total of 32. And then divide by the total of 77. And so then that's how you get that answer there. Yes?
Are you going to do that on the test?
Oh, absolutely.
Yep.
Okay.
Yes,
this is...
Are you also going to do a problem where we do it the other way?
I don't know offhand. That's okay. Probably. I don't know. But, okay. But yes, you have to, that is a requirement. Okay. Next. Okay, so on this one, the trick here, okay, is that you need to find your p-value. And so, and they give you the chi-squared number. So if you're thinking about your chi-squared curve, you know that right here at 0, of course, that means your observed was expected. And so then we've got this going on, okay? And so they tell us that the chi-squared value is 23.5. And they want to know the p-value. Well, the p-value is the probability here of getting that sample or more extreme if the null is true. Okay? And so you can, just like we used to on the normal model, we would norm CDF to get those areas. On this, you chi-squared CDF. So in your calculator, under second vars, you chi-squared CDF from 23.5 to infinity, and infinity for chi-squareds is even larger than just 99 because the chi-squared numbers go quite big. So we go way far out, 999. This might be something you were not sure how to get, the degrees of freedom. Of course, being categories minus 1. So then what you were supposed to notice here is that this was having to do with the birthdays of each month. Hence, there were 12 categories. So DF being categories minus 1, that's how you got 11 right there. So whenever you do that, the calculator gives you a p-value of 0.015, which then is between 0.01 and 0.02. Okay? All right, next. Okay, so on this problem, the frequent question I get is why is this not D? Okay, that we're thinking that each level of job satisfaction is the same for the high school and the college. And so here we go. Here's why. So if you remember, whenever we would do chi-squared test of homogeneity, so when we would do a homogeneity test, then that would happen between multiple populations, okay? So multiple populations, which, let's read this question. What, multiple populations, what are the populations in this problem? Very good. High school teachers, excellent. High school teachers and then the college professors. Okay, so there's the two populations. And then what they're wanting to know is about their job satisfaction. So when they ask about the job satisfaction, we need to see, what's this form of this data going to be? And this form of this data is probably, first of all, this says level of job satisfaction here. And if it was homogeneity, you would just have one category. And so that would be something like you are satisfied with your job, or you are not satisfied with your job. Okay? But I don't think that's what's going on here. They say level of job satisfaction. So it's probably more than just one category. It's probably categories like highly satisfied, or on a scale of 1 to 10 or whatever. So highly satisfied, moderately satisfied, and unsatisfied. So whatever is happening, there's various levels. So there's many categories. So it's not just one category. So it is not a chi-squared test of homogeneity. So it's not asking if they are in the same rate. It's seeing if those two variables, the two variables of the teaching level and the job satisfaction, are independent of each other. Okay, so that's my explanation as why it is not D. Next, going on to the next one, number 4. I kind of think I'm liking B better the more I look at it. I mean, I'll tell you the problem I have with it, but I think if it was a standardized test, then they probably would have B as the answer choice. But let's take a look at this. Which of the following statements are true? So you actually have to go run a matrix. So you do have to go and run the test for this. So I would put this into matrix A, and I would go run a chi-squared test. And when I did, I got these results. A chi-squared of 0. So that means the observed was exactly what it was expected to be, or that those are happening at the same rate, or that those are completely independent of each other. Okay? So the p-value is 1. So let's think about, so it actually gave me a chi-squared of 0. So there we go. So I know it's 2 for sure. Okay, so I can mark out these other ones. Oh, wait, that's wrong. Okay, so I would know it's 2 for sure. But then, now we are wondering about what else is going on. So let me ask you this. What would the null hypothesis be for an independence problem? The null hypothesis is that the two variables are what? Independent of each other or not independent? Independent, because that means not affecting each other. Nothing happening. They are independent. So the null hypothesis is they are independent. The alternative is something is happening. They are affecting each other. They are not independent. There is some connection. Okay, so let me ask you this. With a p-value of 100%, that of course is greater than alpha of 0.05. So what would your decision be when you run this test? You're going to fail to reject HO. So you're going to fail to reject HO. And if you fail to reject HO, you do not have evidence of HA. Okay, so that is why the book then says this. Now, the problem I have with this statement 1 is it's kind of basically saying the null hypothesis is true. Okay, and I'm telling you, the number one, when you get your quiz back, the number one mistake that people did that I am starting to see creeping in, probably a third of the people that got their conclusion wrong. Well, actually, if you got your conclusion wrong, most of the people who got it wrong because they said something like this. So this is the wrong statement that people keep telling me. They fail to reject, okay, and that's fine. I mean, whatever the decision is, that's fine. Fail to reject HO, but then they say this, which is wrong. They say, there is evidence HO is true. And that is bad. Do not, if you fail to reject HO, okay, I get it. HO stays, and that's fine. But let's think about it. If the null hypothesis says O.J. Simpson is innocent, okay? And the alternative says, O.J. Simpson is guilty. Okay, because we know that's what we got going on in the court of law. Okay, so guess what? The real thing that happened in this lifetime, what happened was they failed to reject the null hypothesis. They did not reject this. So, does it mean we have evidence that O.J. Simpson is innocent? Can you have evidence, physical evidence, that O.J. Simpson is innocent? No, you cannot say you have evidence of his innocence. You just did not have enough evidence, so that's the correct thing to say. You have no evidence of H.A. Yep, I'm making it right now. All right, so we have no evidence that H.A. is true. So that's what you're supposed to say. We did not find enough evidence to say O.J. Simpson is guilty. So the bottom line is, people, when you get your quiz back and you've gotten the conclusion statement wrong, and I've written about 5 exclamation points on it, it's because don't tell me you have evidence of H.O. Evidence is always for or against H.A. All right, just my little side step there. Okay, next one. Here, this one's just straight, put it in, do your calculation, and you got your answer, so I'll just go quickly past that one. This one again, this one is knowing that the degrees of freedom was rows minus 1 times columns minus 1, so that was just reading through it, seeing how many groups there were, and counting your degrees of freedom there, okay? So I don't think that one was tricky. All right, next, we're to... Did I do all the ones on that page? Yes. Okay. So now number 8. Okay. Do you have a question? Okay. All right. Here we go. Number 8. So, yeah. This says a condition for chi-squared test is that most of the expected values are going to be at least 5. I don't think that I would go, we have to say all the expected are greater than or equal to 5. Okay, so I wouldn't go with 1. And then, okay, here we go. We know this. Chi-squared goodness of fit has to do with one population and the claimed percentages for those categories. That's true. Okay, how about this? Expected cell counts for goodness of fit is the same as tests of independence, and that's not correct. For independence, remember, that's 2 variables. That's the matrix. So for the independence ones, when you have the matrix, you have to do row total times column total over total. But for the goodness of fit, remember, that's whenever you do list 1 is your observed, and list 2 is your expected, and each one of these numbers are n times the probability, total sample size times the claimed percent. All right, so 2 only. All right, number 9. All right, this is the tricky one. So I think the number one thing that gets everybody on this one is remembering the normal model and the normal model percentages. So here it is. It says it is hypothesized that scores on the certain intelligence tests, like IQ, these sound kind of like IQ ones, are normally distributed with a mean of 100 and a standard deviation of 10. Okay, mean of 100 and a standard deviation of 10. So I drew that right here. So we've got these test scores with a mean of 100 and a standard deviation of 10. So you have to remember back of the normal model. So the normal model has the 68, 95, 99.7, okay? If 68% of data is within 1 standard deviation, okay, then I can tell you, then this section here from 90 to 100 should have 34% there. And that this section from 100 to 110 should have 34% there. Okay. Now, then the problem also says how much is below 90. So it just wants to know this whole section that is below 90. You don't actually have to get into great details, but that total amount that is below 90, this whole section here is 16%. And then this total area above 110 is also 16%. So those are the 4 expected percentages. So that's a chi-squared goodness of fit. These are the expected percentages. So see, look over here. Here is the below 90 was 16%. So 16% of 100 was 16. And 34% of 100 is 34. So those were your expected, and so on. Okay, now on your answer key, this may be missing. There's supposed to be a squared here. This is what's on the formula chart. If you look at the formula chart, which you'll have available to you, of course, on every test. So look at B. It says 10, so that's observed minus expected, quantity squared divided by expected. And then it does the next one. 40 minus 34, quantity squared divided by 34. And then it does the next one. Observed minus expected, quantity squared divided by expected. And then the last one, observed minus expected, quantity squared. Okay, so that's why B then is the answer. So that was the catch, figuring out those expected percentages that follow the normal model. Okay, so that was a pretty tricky one. All right, any questions on that? Number 10. This is a good type of question that you need to know for the multiple choice stuff. You know, it's giving you all these kind of theoretical ideas about goodness of fit stuff. The counts do have to be categorical, and it matches a claimed percentage. That's your chi-squared goodness of fit. Test whether distribution of counts. Oh, numerical. What's wrong with that? Numerical? That's quantitative, and quantitative are not chi-squared at all. Okay, C says if we want to see if things are the same, that's homogeneity. And here we go. We have 2 categorical variables, 2 totally separate variables. It says on that sheet that you have, that's the summary sheet, independence is 2 total separate variables. And again, E is wrong because of the numerical. That's quantitative. Has to be categorical. All right, number 11. Number 11 being a matrix. All you had to do, it asked you what's the expected for the problem solved at location 2. So you just need to find expected for that cell. So that's the row total of 325 times the column total of 161 divided by the total of 500. All right? Question there. So that's your expected that you need to know how to do. All right, then the next one. Here we go on over to number 12. Okay. So this one's interesting. We've got perfect independence. That means they will have the exact same rate. They will have the exact same rate. And because of that, you can set up equal proportions, okay, to solve this. So that was the key that you were supposed to know. So you could set it up this way, 40 over 50 equals 60 over n. You actually could do it another way. You could say, so this is your observed equals expected. So you could set it up this one, 40 over 60 equals 50 over n. Regardless, in both cases, so you could go 40 over 60 equals 50 over n. Either way, they still come up with the same size n. Okay, so that was the key, exact same rate. Number 13, this one I just went and I ran a chi-squared test and I got this p-value, and so then I have evidence of a relationship. So again, on some of the, look here guys, on the test, you need to make sure you have a clear understanding of, think in advance, okay, what the null is and what the alternative is. So here, I'm thinking the null says they are independent of each other. The 2 variables are independent. They are not affecting each other. So they are not related. All right, and the alternative is they are not independent, so something is going on. They are connected to each other and related. So that's really important that you kind of establish that before you even start a problem. Then when you look at your p-value, which is low, you're going to reject the null hypothesis and say there is a relationship. Okay? So once that happens, then you just need to decide if it was very strong or weak. So any idea what that means whenever you're asking if there is very strong or weak evidence? That kind of has to do with, how strongly did you reject the null hypothesis? If you had, and I think some of you were asking me this on the last quiz, if you had a p-value of, say, 0.048, and yes, that is lower than an alpha of 0.05, but what do you think about that? Is that a real solid, dang, that HO is out of there? Is that real solid evidence? Probably not. This would probably be weak because the p-value is so close to alpha. But something that's strong might be if you have a p-value that is really low. So if you had a p-value that's, say, like 0.005, okay, then that's going to be very much definitely lower than alpha, okay? So we had a p-value that was very low, 0.0026, so I feel pretty confident in my rejection of the null. All right, number 14. Oh, here we go. This one was one that you see, guys. Please know on the test tomorrow or whenever you have these kinds of questions, you can't just imagine that you are supposed to know automatically if you reject or fail to reject or whatever. You will have to run these tests, okay? You will have to run these tests to know if you reject or fail to reject. You will have to think to yourself, what does HO say? And so in this problem, what does HO say? That the ratio of 1 to 3 to 3 to 9 holds true. Okay? And the alternative would be saying, you are going to dispute the claimed 1 to 3 to 3 to 9 ratio. Okay, so that's a first, is making sure you know what HO and HA says, okay? So tomorrow, that's what I would do on each problem. Identify what your HA says, then go run the test. So that's what I'm going to do over here. I'm going to come and I put the observed, and then look at these expected. How did I get this 1/16, 3/16, 3/16, and 9/16? How did I come up with that? Good. I totaled these numbers up. The 1 to 3 to 3 to 9, total of 16 parts. That's how I knew my fractions, 1/16 and so on. And then where did this 480 come from? That is the total number of flies. Okay. All right. So once I did that, look, I got a p-value. What would I do with this p-value that is less than alpha? I'm going to reject the claim, and so I have evidence. The test gives sufficient evidence to reject the geneticist's claim. All right, so if there's anything that you get from this, going over this part of the review, it's that you have to identify HOHA, then go run the test so you can decide what your decision is. All right, number 15, this one's pretty straightforward also. Putting in all your information and then knowing the formula. Where do you find this formula? Where is that formula located? Do you have to have it memorized? That one you do not. This one is on your formula chart. Okay? All right, moving on. Number 16. Okay, again, HO for this one is that they happen at the same rate. HA would be not the same rate. Okay, so look here. How many populations is there in this? I just have one set of observed data. So what kind of test is this going to be if I just have one population of data? Yep, goodness of fit. So since I have one population of data, I'm going to have a goodness of fit. So it should give me percentages. But it didn't give me percentages. So what the heck? What do I do if it doesn't give me percentage? What did I do then? It asks if they are happening at the same rate. So then, and I knew I'm going to do even. So I took the total of 165, divided it by 3, and that's my expected. So I did that in my calculator. L1 for the observed, L2 for the expected, and I ran a chi-squared goodness of fit, and so I get, wow, look at this p-value. Is this strong evidence or weak evidence right there with that p-value? That is a low p-value, so that HO is so out of there. Okay, so gone. So that's strong evidence. So I have evidence to reject the null hypothesis, and that's what A says. What does this mean? At the 0.001 significance level, what does that mean? That's the alpha, good. So it was significant at the 0.001. What would this mean? Look at this. What would this mean? 0.10 level, but not at the 0.05. What does that kind of a statement say? That you have something significant at the 0.10 level, but not at the 0.05. What would that mean?
That's on the normal model where at 0.10 it could be here, but at 0.5 it's there.
So maybe. So, okay, so something like this says your p-value is lower than 10%, but not lower than 5%. That's what that means. So it's significant at the 10% level, but not at the 5% level. Okay, does that make sense? It's lower than 10%, but not lower than 5%. So you just have to see, where does your p-value fall? And mine was lower than all of them. Okay. Number 17. So for this number 17, again, looky here. Look at how I'm starting this thing. I'm identifying my HOHA. Okay, and then I'm going and I'm running the test. And I see what I look at that p-value. It's quite large. It is greater, of course, than an alpha. So I will fail to reject. So okay, hey, you people, listen up. If I fail to reject HO, do I have evidence that HO is true? No. Evidence is never about HO. So you say, I do not have evidence of HA. So I have no evidence of whatever HA is. No evidence. And so that's what this says. No evidence of HA. And HA is a relationship between them. Okay. So that's the thought process you go through to accomplish these multiple choice questions. Okay, number 18. Again, this was... Okay, so at first it bothered me that they called it homogeneity whenever we have 3 different professors and multiple categories of grades. What have I told you that we should call that? Yeah, independence. We got 2 full variables there. So anyway, but same thing. Decide what your HO is. Oh, look at there. Chi-squared homogeneity is not appropriate for a couple of reasons. First of all, it's high independence, but also look at what's wrong with these expected counts. Yes, there are some of them that are not greater than or equal to 5, so that's a problem. That's why the homogeneity is a no-go. I mean, well, any of them's a no-go, but anyway. Okay, number 19. Which of the following is not true? The expected frequency do not have to be a whole number. Why? See, looking over here, why do these expected numbers don't have to be a whole number? Very good, because the expected value is the mean. That's what we expect to happen on average. Okay? Very good. And then this last one, number 20, I have it on here sideways, so it's kind of hard to see. But basically what you do is, again, you take this matrix and you figure out from this matrix on number 20 what the expected values are. And then, remember your formula, you sum up, what's the formula for chi-squared? Observed minus expected, quantity squared over expected. Okay, sorry, that's sideways. Okay, so then I just followed it, 33 minus 44, quantity squared over 44. Okay, and then the next one is going to be 77 minus 66, quantity squared over 66. And so on. And the third one will be 47 minus 36, quantity squared over 36, and so on. And so you just find the one that has the correct fork. All right, done with that. So in summary, make sure that you go over your little chi-squared summary pages that I gave you, your chi-squared summary pages. You remember, and that's that blue sheet that has the difference in them all. Remember how you get expected values. Remember standardized residuals formula, which is on that as well, and so on. Okay, so go through those. Again, it is all multiple choice, no FRQs, so that's nice.